This is part 3 of 5 parts of the hypothesis testing lecture. The focus of this part is on the test of central location. To test the central location, we could use a z-test where we compare the sample mean with the hypothesized value of the population parameter divided by the standard error. The standard error in this case is the population standard deviation divided by square root n. That's all well and good, but we rarely know the population variance. So we will resort to a t-distributed test statistic that has n-1 degree of freedom. The t-distributed test statistic also compares the sample mean with the hypothesized value, but in this case divides by the standard error, which is constructed by taking the sample standard deviation divided by the square root of n. So this is a parametric test, as all the tests that we're studying in this segment. There are some non-parametric tests, such as the sign test and the Wilcoxon sign rank test, and they test whether the median is different than 0. But our focus is going to be on the parametric tests, which have more power. So suppose we collected data on equity returns across a 48-month period, and we have a mean of 12.94% and a standard deviation of 15.21%. So we have a sample size of 48. And suppose you want to test whether this average return is equal to 15%. And you want to be 95% confident in your results, which means you're going to have a level of significance of 5%. So what we do is we construct the null hypothesis. In this case, mu is equal to 15% versus mu not equal to 15%. We identify the appropriate test statistic, which is the t-statistic, and we have the level of significance of 5%. So this leads us to the critical values of plus minus 2.01174. We can get these from Appendix B, where we use half of the alpha, because that's how the table is designed, or we could use Excel or our calculator to get the critical values. We collect the data, which we already did, and then we calculate this test statistic, and we end up with negative 0.938337. In this case, we fail to reject the null hypothesis. So the 12.94% that we see in our sample is not different than the 15% that we hypothesize. So it's not going to affect our forecasts. Now, if you want the critical values in your TI-83 or 84, you use the t-interval and you use the mean of 0, square root of the sample size as the standard deviation, and n for the sample size. And this will produce the critical values, the plus and minus. You can do this in Excel as well. In this case, you'll see the critical value we calculate using the t-inv function, and the p-value calculated using the t-dist functions. And I would suggest that you try doing this just to make sure that you know how to execute those calculations. We can use confidence intervals to also help us with the decision. If we have a 95% confidence interval, remember what we do there. We take the sample mean plus or minus, and then we've got the product of the reliability factor, which is, in this case, a t factor, times the standard error. So we insert the known information into this, and we end up with an interval from 0.08523 to 0.173565. Because the interval contains the 15% hypothesized population value, we fail to reject the null hypothesis. So let's take a look at another test. Here we're talking about the VIX. What we want to do is test whether the mean VIX is greater than 18. We collect the daily VIX index values from 2004 through March 12, 2020, and we have calculated values of average of 18.26453 and a sample standard deviation of 8.678562. And we want to test whether that mean is different than 18. And in fact, we want one-sided because we're asking whether it's greater than 18. We have a 5% level of significance. In setting up the hypotheses, we set up the alternative first. That's dictated by the wording of the problem, and then by default, the null is everything else. The calculated test statistic in this case is 1.94598. The critical values for 5% one-sided is 1.645. So if we were using the appendix at the back of the book, what we'd look at is the heading for 0.05 because that is the one-sided area in the probability curve. The p-value, if we want to calculate that using Excel or a calculator, is 3%. So what we conclude is we reject the null hypothesis. So what we're saying is, very casually, we say that the fix is greater than 18%. We can't say that definitively, but we can say that it's not less than or equal to. We can look at this graphically. We can see the cutoff right here, the critical value is the 1.645. That comes from the table or calculator or Excel. And then we have 5% area under the curve, which is that red, and that's the rejection region. And going back, if we go back, we have 1.94598. If we go look here, that would be in the rejection region. It falls in the red area, so we reject the null hypothesis.